Hello. So, in this video we are covering what is pretty universally decided to be one of the worst things about having to do polynomials, which is the glorious rational root theorem. So this is really a tool of last resort, and we will see why in this video, but it is a tool to find sort of potential zeros of a polynomial. So before we sort of dive into it, a couple observations are sort of helpful. So if we have sort of a very basic polynomial, almost as basic as can be here, right? We have a nice line, ax minus b. Well, finding the zeros for this, nicely straightforward, right? Set it equal to 0, move the b over, we get that the 0 is b over a. Pretty straightforward. If we go up sort of one level of difficulty, right, go to our nice quadratic, and we sort of saw this when we talked about the coefficient method, although this one now has some leading coefficients. But nonetheless, if we do something similar here, right, if I have this sort of, I know that this sort of nice factored form already, I set each of these things equal to 0 and sort of solve, I get that the zeros are b over a, right, from the first thing, and then d over c from the second one. Okay, big deal, why do we care? Well, the observation that is sort of nice to make here is that in both of these cases, and in fact this will generalize sort of very nicely, is that the zeros of these polynomials have this relationship where it involves one of the factors of the constant piece, so b in the case of my first one, or b times d in the second one. So I'm going to take one of those factors, and then I'm going to be dividing by a factor of the leading coefficient, right? So in this case, a up top, or this a times c down there, right? So in both these cases then, these zeros of these polynomials are a factor of the constant divided by a factor of the leading coefficient, which is great-ish, right? Like, how do we use that? It's a nice observation. Why do we care? Well, let's look at sort of a concrete example, at least to convince ourselves that this thing sort of works in a more clear way, right? Like, we're not a big fan of alphabet soup. So if I have this thing, well, I can factor this, right? AC method or whatever you want to use. I'm going to get this 2x minus 3 and this 5x minus 7, which gives me zeros of 3 over 2 and 7 over 5. But again, notice, right, that 3 and 7, both of these things divide 21. 2 and 5, both of those things divide 10. This thing sort of works under at least these circumstances. All right, so with this sort of motivating observation, I'm going to go ahead and give you the sort of math version, and then we'll talk about the human version, right? The math version of the rational root theorem. So the rational root theorem, or RRT as we usually refer to it, because that's a long name, says that if we're given some polynomial, right, this very sort of generic version, but all the coefficients are integers, that's important, right? So they're all nice whole numbers, positive, negative, maybe 0. If there exists, again, I want to draw sort of real emphasis to the if there exists integers a and b such that ax plus b is a factor, meaning that b over a, or in this case minus b over a, is 0, then a has to divide a of n nicely, right, evenly, and b divides a sub 0 evenly. So a nice sort of way of summing this up is that if we have a 0 for p of x that is a rational number, then it's going to be of the form a factor of that leading coefficient divided by a factor of that sort of constant, okay? All right, so how do we sort of use this? Well, the thing is that this allows us to generate a list of possible zeros. So it doesn't necessarily find the 0, but it allows us to sort of narrow it down from infinite possibilities to at least some sort of list. The thing is it only finds rational number zeros, okay? So for example, if we have something like x squared minus 3, rational root theorem would say that the possible zeros are 1 or 3, because it's a factor of 3 divided by a factor of 1. That gets me 1 and 3. Neither of those are zeros of this polynomial, though, right? Like, we could plug in 1 squared is 1, minus 3 is negative 2, not 0. If I plug in 3 squared is 9, minus 3, 6, not 0. And that's because the zeros of this are plus or minus square root of 3, not rational numbers, okay? So it's important that this thing only finds rational zeros. Nonetheless, that is something. So as an example, right, as a sort of concrete, fully worked out version, what if we had this admittedly annoyingly large polynomial, right? Well, rational root theorem says that we could find the potential rational zeros as factors of the constant divided by the factors of 84, which is the leading coefficient. Now, I mentioned that this is a tool of last resort. We'll see why in a second very clearly. But to be clear, we would want to try to factor this any other way we could. Unfortunately, it has 5 terms. We can't do by grouping. There's no quadratic form hidden here. There's really not any other options. So we really are stuck with rational root theorem. So to do this then, well, we start by generating a list of all these possibilities, starting with all the factors of 30 and all the factors of 84, okay? So writing all those out, I have all the factors of 30, all the factors of 84. Now I want to form every possible number that is a factor of 30 divided by a factor of 84. And remember, we also need plus or minus, right? Because it could be a positive or a negative root. So if I do that, I get this monstrosity. Oh boy, right? Better than having infinitely many options, true. And in fact, it's not quite as bad as it looks because we can reduce it a little by, cutting out repeat versions, right? So for example, 10 over 2 is the same as 5 over 1, so I don't have to have that in the list twice. But that only gets me so far, right? And this really is why rational root theorem is a tool of last resort, because even sort of doing this, sure, I don't have infinitely many numbers to like throw a dart at and guess, but I still have 98 numbers to throw at a dart and guess, right? There's still a large list. And a perfectly reasonable question is, okay, which one do we choose? How do I know which of these is the right one, is the 0 that I have to use? And the honest answer is you don't. You really do, in some sense, throw a dart. Now, in fairness, as you do this a lot of times, right, as you practice this more and more, you do build intuition for some being more likely than others. But it's not a perfect system. Like, you're still sort of guessing out of those 98. A follow-up question might be, okay, what if I'm going to guess 1? What if I guess 5? How do I know, right? Well, if I want to guess 5, I could do 2 things. I could plug in 5 and actually calculate it, but doing that is kind of annoying, right? 5 to the 4th times 84, that's going to be a really obnoxious number. And the thing is if it is a 0, I'm going to want to factor anyway. So an easier way to go about this is to instead use something like synthetic division, right? So if I think, okay, well, if, is 5 a 0, put it into the synthetic division, run it through, check the remainder. Remainder's not 0, so 5 is not a 0, right? Go back to our list, do it again. That really is how it works. So instead of 5, right, not a 0, well, let's try the factor 2x minus 3. And this is sort of useful because this is sort of a useful little subsegment here, because the factor would be something like 2x minus 3 in order for this sort of thing to look nice, right? Because that's going to have a leading factor of 84 and it has that like last constant of 30. But the 0 that I'm checking, if I'm going to use synthetic division, is actually 3/2. And this is sort of an important distinction. So if I check 3/2, well, putting it in, run through the synthetic division, aha, right? Remainder is 0, that tells me 3/2 is 0. But that's not factoring out the 2x minus 3, that's factoring out x minus the 0, the x minus 3/2, right? Where the remainder part, this whole thing, is what I got from the synthetic division. Now, I could clean this up by factoring out sort of a nice number from the remaining part, right, from this 84x cubed bit. I can factor out something that I can cancel out the fraction over here, meaning that I can factor out a 2 from there, so that I could then multiply that 2 into the first bit, and that would give me that 2x minus 3 factor to sort of rewrite it in a nice way. And in fact, this is actually worth doing not just so it looks nice, but because when I then look at this cubic, factor by grouping still doesn't work, which is bad news for me, because that means I'm probably going to have to do another rational root theorem. But Because I moved that 2 over, I now have different numbers, right? I have a 42 and I have a 10 instead of that 84 and 30 or whatever, right? So as a result, I want to make sure to generate a new list, right? I want to do this factor of 10 divided by factor of 42 instead of factor of 30 divided by a factor of 84. Because A, it'll be a smaller list, but B, remember that if something was a factor before, it's still a factor now. And if it wasn't a factor, like 5 before, it's still not a factor now, meaning that the list that I'm going to build is going to be a strict subset, okay? If I have the same numbers, if I still somehow had 84 and 30, for example, I might still get the same set. So it may not be strict, but as long as I've sort of moved the numbers down somehow, I should get a strict subset. So that means that I'm going to go from this list, right, my 98 that I had before, and I can shrink it further now by using the 10 and 42 and get down from 98 to 48. So even though I've tested one unsuccessfully, which I think I actually still included in this list, so really I have 47 to check. But nonetheless, I have one that I tested unsuccessfully and one that I found. So I've done 2 tests, right? I've checked 2 factors, but somehow cut out over 50, really 50 plus the 5 that I didn't, keep track of. So I've cut out 51 possibilities by making this new list, right? So again, I want to really hammer home here that the idea is that you don't want to use the same list, because every time you do a step successfully, you get to cut down the list dramatically, right? But still, right, I have 48 ones to go through, or 47 if I'm getting rid of 5. So I just pick another one, right, from the new list, because at least now I know there are 50 of them that don't work that I never had to check. But still, I still have to, plug in another one. So I could try 1, again, picking numbers sort of seemingly at random. Not really, because I don't want this, video to go on for 6 hours. Turns out 1 works. What a shock. Right, so 1 works because the remainder is 0. That means that 1 is a 0. So I have, again, the thing I started with, right, the original polynomial, which I did factor 1 time into this 2x minus 3 and then that 42x cubed piece. But now that 42x cubed piece, I can factor out the x minus 1 and get down to 42x squared plus 47x plus 10. Now, you may look at that and go, but I still have 42 as a leading term and 10 as the constant term, so I haven't made my list any smaller. Which is technically true, but completely missing the point. Because again, rational root theorem is a tool of last resort. You want to avoid this at all costs. You never want to use it if you can avoid it. And guess what we have now? We have a quadratic, right? The quadratics have all kinds of other ways to factor. So you should not be using a rational root theorem to factor the quadratic. You should look at that and go, thank God, I don't need to use rational root theorem. I don't have to check 46 other numbers or whatever. I can just go ahead and factor that thing directly and get that it's 7x plus 2 and 6x plus 5. And if you're curious, I'm sure you could go back to your list and see that indeed, right, 2/7 and 5/6 were on there somewhere. And so we could have gotten these eventually, but there was no reason to go back through and start checking all of those other numbers, right? All right, so rational root theorem, this is only ever a tool of last resort. It's sort of a desperate last sort of guess measure, so that instead of throwing a dart at all of infinitely many numbers that might be roots, we're at least throwing dart at a finite, if usually very large, list of numbers that might be roots. Each time we check a factor, we want to use something like synthetic division or polynomial long division, really because A, that's going to show whether or not the remainder is 0, meaning whether or not it is a 0. But if it is a 0, then as a bonus, it gives us the factored form right away, right? Whereas if we're just plugging numbers in, it's not necessarily, right? That's not going to give us the factored form if it is a 0, so we're going to have to go do long division or synthetic division anyway, right? So this is sort of a very handy way of killing 2 birds with 1 stone in most of the cases. Plus, a lot of times synthetic division is easier than actually doing the computation, especially with large powers. Once we do find a 0, we want to extract that factor, right, using long division or synthetic division. Then we want to try to factor the remaining polynomial, the thing that we have left over, using any other method, right? Rational root theorem is terrible. I know you're going to be like, wow, this is awful. Why do we have to do this? And you're going to come to me and be like, is there any other way? I'm going to be like, no, because it really is that terrible. It really is a tool of last resort. That's why you try to avoid using it whenever you can. It's just that sometimes you really have to use it. There's just not another option. If we still need to use rational root theorem, then that's really unfortunate. But if we do have to use it, make sure that you make a new list, because that list should be a subset, which means you can cross off anything on that list that you've already checked. And usually it is a smaller subset, right? It's a strict subset. It's got fewer things to check. And to really hammer this home, don't keep using the same list. Don't check all of the options, especially when you get down to something that is like a quadratic, where there's got to be a better way, even if it's doing something like completing the square or quadratic formula or something to force out the factor. Like just don't ever use rational root theorem on a quadratic, because it's just causing you lots more pain and suffering than you need to be going through, right? Tool of last resort. Don't do it unless you have to, okay? All right, so what did we talk about? Well, we introduced the glorious rational root theorem, which is a way of going from infinite possibilities down to a finite number of things to check for specifically rational roots. And that's sort of an important caveat, because there are polynomials that don't have any rational roots. So it is technically possible that you could have something where you have 98 rational values to check for, and you do synthetic division on all 98, and you don't find a single zero. I will not do that to you. But I am saying it is technically possible that that could happen, right? So it's worth remembering that it is only for rational roots. But I mean, it's terrible going through that many different possibilities, doing synthetic division on all of those things, or long division on all of those things, one by one, hoping you haven't made a mistake, and, getting through all of that long list and wondering if it's because there aren't any rational roots or if you made a mistake on one of them, right? So this is always a tool of last resort. Try to do any other option before you do rational root theorem, because rational root theorem just takes a long time. So always go back and check, all right? So that is that.